נבדוק אם שומעים אותנו. Okay, let's get started. First of all, disclaimer, you probably know I'm not a native speaker when it comes to English. So pronunciation and any typos, forgive me. Couple of things we need to say before we actually start learning. I'll say everything and probably remember something else when we go on. So first of all, we have two lectures every week and one practice with Neil. Avanti was last semester. He's a good guy. Yeah. So keep going. We have some breaks. I'll tell it this Tuesday with something with show or something like that. I don't know. Yeah. פתיחת שנה between 12 and 2 p.m. It actually falls on linear algebra, but I want to check with the secretary if we can change it so we have a full lecture of linear algebra on Tuesday, and we will give up on one of the infis. We have a lot of infis, so it's it's better that way, but I don't know if we can actually do it. I asked them and wait for the answer. No, it's Tuesday. Now we can wait. Hanukkah, one lecture I think is going down. Asara B'Tevet, Tuesday with 2.5 months something, but right now we don't need to schedule additional lectures, no practice. But if we actually do, so we make it like grown-ups, not something very terrible. Of course, with Zoom, actually, we have a Zoom. You have a Zoom link if you want to come, online and not to be here frontalit. And as far as I can see, you are 5 people in this class. I mean, you are 3, but another 2.
Yeah,
over here.
about that, I think like if we also saw that 5 people signed up, I'm hoping that they all got the okay from the university, but I don't know, like if in the end, no, or who signed up? Do you have the list?
I think I am. It's not that important, but
It's really not that important. We do that in class, right? No, Lev didn't pass as one. I don't know if Lev did.
the only thing I want to say about it that's we have here Thomas, Sami, Rafael, Ariela, and Lev.
Ariel.
Ariela.
Yeah.
Ariela Stefanski. I don't know. Right now you're 3 here and Lev is on the Zoom. Um, it's totally fine, of course. The only point about small numbers is if you feel like not coming today.
Which time exactly? No.
Why not? Why not? Why not? Why like this?
בעברית זה בשתיים.
בעברית זה בשתיים. זה אותו חומר אבל בגדול.
כן, הבנה שונה.
Started to say, if you feel like not coming today, not in class and not in Zoom, just tell me. Because if it happens that all 4 of you are not planning to come, well, I will not be planning either.
We have your email. We have your email on Lambda.
Yes, you can do it. First of all, send a message to the Lambda. Secondly, my email. Of course, if you type a lot of PMA, Google, you'll find it. You mentioned the Lambda. In the Lambda, there I put 3 links. One is to the Zoom. Second, to notes and recordings from previous years. It's in only Hebrew, but with GPT and all the friends, you can handle the thing. And the third one is for a WhatsApp community, which is also in Hebrew, but you can join Infish time, Linearish time, or whatever course you want. And they're trying to be as much as available as I can to answer your questions. When it comes to a course that I teach, Infish time, Linearish time, I can answer whatever question you have, not just about the material himself, but also all the technical points, lecture is on. I want to submit the homework late or something like that. When it comes to the course that only know the math, let's say Istamrut, for example, you can ask me whatever you want when it comes to mathematical questions about the Other parts of course, I cannot help. If we mention the homework, we are not going to have a midterm exam this semester, probably all very upset. But when it comes, yeah, well, sorry, devastating news. But when it comes to homework, we do have homework, let's say every week or something like that. Probably they're going to be like 10 or 11 homework to the semester long. It's all in the news responsibility. If you want, to submit late or something like that, just ask him. And I told him to let you go. We need, we need to submit something. It's fine. You're a small group, so I don't think it's going to be a problem for a lot of people who want to submit like. But all the questions about the homework and what's around it, you're gonna ask Nir, and you're gonna explain it very well. I don't know, I don't remember when the practice is. Sunday, Tuesday, today, so it's fine. After the lectures, it's totally fine. Okay.
Will the homework count towards our grade?
What?
Will the homework count towards our
Yeah, yeah. I don't remember the precise. I think it's 10%. 10, maybe 15, because you don't have a middle exam, and I want the homework to help you going through the semester. But needs to be said, if you don't pass the final exam, the homework doesn't count, as far as I know.
Mm-hmm.
I mean, you have to get at least 60 or 56, depends on the situation, in final exam, and then the homework can help you with their 15 or 10% from the final grade. One more thing before we actually start the material himself, and probably something on my mind I don't remember right now. A common question when you come to a course with the number 2 in his name, in fish time, linearity time, how much do we need to remember to know the material from Infi Echad? So let's put it that. Of course, you don't need to know the material, to right now solve an exam or something like that. You don't have to be afraid from Infi Echad. I don't know who taught Infi Echad. Erez? Erez, well, very best lecturer in the university, but I think if you are here, if you are all here, it's fine. And you don't need, again, to know exactly every point, every spitz in Echad. On the other side, if courses were totally not connected, it wasn't called a P2. So what do I expect you to know? And of course, you can ask me whatever you want and I'll explain. First of all, the basic notion, like what is the continuous function and stuff like that. And secondly, the basic theorems. For example, if you take a sequence that tends to 0 and you multiply it with the bounded sequence, the sequence you get also tends to 0. Called the תפיסה כפול חסומה in Hebrew. The more complex theorems, like Lagrange mean value theorem, when we are going to use them, I'll write them on the board and we'll discuss if we need, remember what we need to remember. So that's about the connection between Infi 1 and Infi 2. Any other technical, administrational questions? Yes.
Technical, I think it's this class, the first one, we're going to talk about trigonometry, connected to what we're going to learn.
Trigonometry?
Yeah, I don't know that. I think there's more trigonometry on this time than the but like I don't know how much we need to know from start.
No, just the basic notions. Sinus, cosinus, sinus squared plus cosinus squared is 1. Maybe not. Cosinus of 2x. Okay, nothing more. No, not more than if you want, of course. No. Other questions? Zoom, how are you, Lev? Can you hear us? Don't know. Did you speak? With the chat. All right, yes. All right, come on. So, What are you going to do with math on this lecture? Um, it's natural way to continue from Infi 1 after you finished the last course with L'Hopital theorem and used a lot of derivatives through the finals theorems like L'Hopital, Lagrange, Cauchy, and all the rest of your friends. We are going to start and talk about integrals. The second part, the derivative is the queen of calculus, so integral is probably the king. And we're gonna have, let's say, like 10, 11, something like that lectures about integrals before we are going to the next subject. Oh, it's another point I wanted to say. I don't know exactly what happened in if you want. I wasn't there. So sorry for it. There was a good lecture, but the course is if you want, the course, if you want has like one course, one way to go naturally from bounds to sequences to series to functions. Here, as I said, let's say 11 lectures about integrals, natural way to continue from where you stop. But then we're going to talk about something a bit different, sequences and series of functions, which you can, after you learn the basic notions of functions, you can start from there and not from derivatives and integrals. And after we finish that, I don't know exactly what number the lecture will be, but we're going to talk about calculus of two or more variables. And after we done a very exhausting job when it comes to one variable, then we're going to take now 5, 6, maybe 7 lectures about calculus, multivariable calculus. But probably we'll focus on two variables. So in that way, the course is actually built from 3 parts, not very, not very connected to each other. Of course, in the part of multivariable calculus, we'll use derivatives, and we talk about sequence of functions. We'll use integrals, but it's not. It's sometimes it seems like it's again 3 different parts, and not one monolith big course. And I don't know if it's a good thing or a bad thing, but you have to remember to do we'll do it, of course, here in exactly as well, the shift from one subject to another when we get it. I just want to say it's, from my point of view, it's like the course comparing to one is still a little less well, because you have for comparison, I used to teach the courses in AJT, if you know this place in Poland. Alone Institute of Technology. I call it, it's, let's say the level of study is a bit low here, lower, but it's a good place nonetheless. And there they have 8 hours weekly of into one. No 4 lecture to practice, but 5 and 3. So they have, more time to learn all the stuff we want to learn there. I also teach, that's where I'm סגל בכיר, I don't know how to actually say it in English. In College of Management in University of and then there they used to have Inti 1, Inti 2, and Inti 3. A small course, 2 hours lecture for practice. And now they have some different name, subjects in advanced math, like that. And AI in AI, yes, AI in math. It's actually a big kind of a deal. All the, at least the talking about AI as meetings and what are they going to do. Then how to do it. But here, university, that's better for us. We have like only 2 courses, 4 hours lecture, and 2 hours practice to try and learn all this material, including the multivariable calculus in the end. So it makes it try, and again, look, not exactly what the boards are looking for, but again, less build less well than if you want. It's gonna be fun. Don't you? But we're gonna take a big shift from one subject to another 2 times along the course. Let's say lecture 12, a lecture 10. Before I started Reminiscent this thing. Well, okay, let's start the math and we talk about integral. I'm used to Hebrew. We should start from there, right? However you want. I think it's better. You can see okay-ish. So we'll start, let's say, three, maybe a bit more lectures about indefinite integrals. Integral לא מסוימים, it's called in Hebrew. And the question is simple. Probably you saw it in high school or something like that. We have a function and we ask ourselves, okay, what function should we derive to get this function here? It's called the antiderivative. Question. Here is f. Can we find a function f such that f is, you know, little f or something like that. If bigger than f, and we can estimate, you know, generally or actually for specific domain, let's say in the segment between 0 and 1 or something like that. So one can write f tag x and fx for all x and I for some I, you know, between a and b. It can also be for all the randomly. Simple to state the question, but it's much harder to answer it. And to answer it, it seems like the other side of derivatives, integral and derivative, are the opposite in some manner. But we see that at least technically, it's much harder to find this big F comparing to find derivative of one little f. And I'm going to mention it in a couple of minutes, but before that, I just want to state the name of F Gadol. F Gadol is called antiderivative of F Gadol, the anti. Probably can write it in one word. In Hebrew, it's called the keduma. No, it's not actually the same word. How do you say kadum? Like Gary. No, like I can't throw the previous. And it's a primordial, something like that. The exact translation, which is probably not so antiderivative is the notion we go with. That is called antiderivative. And first of all, we know, let's say for example, some bell. For let's take a simple function, x squared. Can you name an derivative? X squared, x squared. Oh, I think two. Yes. Who's gonna be F Gadol? When we derive F Gadol, we get F Katan.
Oh, it's actually let's start divided by 3.
Yeah. That way? When we derive it, the 3, because people jumps out and cancels 3 in the denominator, is we know that it's not the only one. Yes. Generally, when it comes to this specific example, of course, yes, we add a plus c, and we actually cover all the antiderivatives of f is equal to x squared. So first of all, what we can take on this example, we can ask our question more precisely. It's not just a function. Find a function. We can find the whole family of functions, all set of functions, whatever, that are the antiderivatives of the f. And secondly, you said plus c, which is extremely correct. But we know, and it's not so clear, we're going to explain it now, that these are the only antiderivatives. In other words, when you have two different antiderivatives of the same function, the difference between them is a constant. Not be like it's the power of 4 or sinus or whatever. The difference between two antiderivatives of the same functions is always a constant. Let's state that and prove it. And then we can go on about how do we start to answer this question. Teana, you say proposition?
Yeah.
Then let's go with this. Proposition. Yet again, a typo or something like that, you can feel free to correct me. Proposition. Let F, big F, and let's say big G, great G homing, be antiderivatives. Be English has more letters. Yeah, my grandfather, he used to work at the bank, and he was in charge of the advertising department. So we used to write letters and posters, advertisement, not just Hebrew, in English and French and other languages. So they had this specific numbers. English is, let's say, between 25 and 30% more letters than Hebrew. The French is even worse. It's more than 40%. When you write 100 pages in Hebrew, you need to write 143 or something like that pages in French. Just because you have more words. And in French, they are, in English, the way you write it. In French, they just seem, let's put another X there. Why? Because, without profanity. Yeah. Let the G be antiderivatives of the same function f.
I have German.
What's that?
German as well as, yeah.
Oh, I don't speak it very fluently, German, but I do have the Austrian citizenship. You say Austrish, the German. Yes, it's a lot of letters, but it's a bit different because they have this weird habit of combining words to one big one. And here, let's say it's the word derivative, and we have the plural, and you have the prefix anti. Okay. But there you want to say the bus that comes early, you can read one word of the bus and coming in early, and not just 3 or 4. And there is the same F, then the E, right? Then F means G is C for some constant C. Okay, let's prove it. It's not a big deal, but it's not totally obvious on the other side.
Yeah. Can we use in this context a function, like saying there's a function from the antiderivatives to the derivative, like f and g are part of a set, and if it's a part of the image, and we can say like we can, as by contradiction, it's inductive, or
We can try. After the proof, I write some notation. There's well known the integral itself, and the integral itself is actually not just one function, but a set of functions, or a set of derivatives. And you can think of derivative as a function from the set of sets of functions to the set of functions which take all the derivatives of one function to this function. You can think of it that way. But not, as we know, well, derivatives, not every function has derivative. And we're going to see in this lecture that, on the other hand, not every function has an antiderivative. But it's more complicated than only stable. So let's look at the proof. It's probably a few lines, not something important, but that's right there nonetheless. What do we know? We know that what is another word? Derivative of f big is f little, and f of 15 is f little. So they're both derivatives of the same f. So now, if we look at the derivative of difference between f and g, we know, not just simply one, but probably school, derivative of some derivatives, and they're both f, so f minus f is 0. And what do we know? And that's from the previous course. If not, so we'll expand the explanation. When the derivative is 0, the function itself is constant. Yes, it's if and only. Uh, well, the self is constant. F of GC as we see. It's a good point to say that I used to write, I'd say a lot on the board, but I write. Put it that way. If you're not a fan of writing yourself, don't try to, catch me up or something. There's a lot of mentioned notes in this drivelet I put in the Lambda. But if you want, half a minute to copy the things you write on the board, that's totally fine. Yeah, it's not good.
Sorry, why would f minus g be equal to 0? Because like we say f and g are the same, but shouldn't c cancel out then?
No, f and g are not exactly the same. They are the derivatives of the same function. So
Oh,
just when you derive them, you get the same function a, and then the difference is 0.
okay. The the difference is the difference between constant of s and the constant of g.
It's probably not 0. It's a constant.
Okay.
When you derive the constant, you
Yeah,
get
no,
0.
it's c, but it's a constant that is neither in f or in g. It's just that the difference between the constants.
Yes, so between in both of them. It will be f is the exponential plus 1, and the second one is plus 2.
Yeah.
Yes. So the bottom line is the difference between two antiderivatives of the same function is actually a constant, so we can write now the right notation is, we know it, the integral of fx dx. The d has its meaning, of course, has its meaning, but let's just say that when you come to the multivariable calculus, when you have x and y, and you have the question, okay, by which variable I'm going to integrate now, so we denote the dx, integration by x and dy the integration by y, etc., etc. It's f gadol plus c, and the c is c, and it's not a specific constant. It's the constant of all constants that are possible to put here. And as we mentioned, every constant in R in the real numbers is good. Questions? Lev, you got a question? I can look at you. Okay. So let's get technical. The question is, how do we find an antiderivative for a given f? A good way to say that in these first 2 weeks, in order to going on with the material, as I mentioned, we have a lot of material to speak. Some of the concepts, some of the methods of finding derivatives that we'll see here are not going to be shown in practice and vice versa. In other words, these first 2 weeks, the practice is going to, let's say, complete the lecture and not just practice what we study here. So in order to grab the whole material and not let it go, these first 2 weeks, as I mentioned, 3, maybe 4 lectures, are going to be a bit practicey, yes, with examples and stuff like that. So we don't run with material. Finding an answer derivative. How do we do it? I want to put that question in, let's say, 4 types of functions. Okay? There are 4 types of functions we can ask it for this question about. And it's actually very interesting only when it comes to, let's say, let's put it the last and for the fourth part, we see. Fourth type, we see. We can say you can divide this question to 4 sets of functions. First of all, 1, 2. אינטגרלים יודעים, instant integrals, probably. Like instant ramen or something like that. There are some basic functions, just like in derivatives. When you start to learn derivatives at school, you go, x to the power of n, how to derive it, and sinus and cosinus. And in phi echad, you probably, after the definition of derivative, you started with a long journey of proving that the derivative of sinus is cosinus, etc., etc. But we can have them in a list in which all these instant integrals are shown. Let's just
for integral, there are no definition like for derivatives, where for a derivative
the limit of
limit to going to 0 of h or the difference.
We define the indefinite integral with the derivative. The integral f Leo is the antiderivative. The function is when you derive it, you get it.
Sorry.
Yes, when let's say lecture 4, it's next Tuesday, we'll get to the definite integrals, which are connected to calculating the area between the function and 2x, the x-axis will have a definition. And it's going to be a bit complicated compared to definition of derivative. But now we define the indefinite integral b with derivative. Fine. Together. So infinite integrals, what do we know? Let's say I the integral of x to the power of n, x to the power of n plus 1, divided by n plus 1, plus c. And again, the question is, I want to, if we derive this, do we get that? So we derive that n plus 1 jumps out. Exactly cancels the n plus 1 denominator. This is true for every n except 1, minus 1. Minus 1. What happens when minus 1? The integral of x to the power of minus 1, which we used to call half x. What is it? What function do we derive to get this? It's the logarithm, right? Plan x, but first of all, the plus c, which is always here. And secondly, the absolute value. Without further discussion, this function is defined for every x set, and this function without the absolute value is defined only for the positive x. So we want to keep the domain of the function and the derivative the same. So we put this absolute value, and of course, one can check if you derive this, which is need to be checked in two cases, we need to be positive, we need to be negative. He gets actually in both cases after x is needed. So this is x to the power of something. Two. On the other hand, there are functions who, let's say mathematically, do not have an antiderivative. Not right. Why? Function and that. Did you see Darboux theorem last course if you want? Darboux. Another dead French one. Like the rest of them.
Like the rest.
Like Cauchy and Lagrange and Lagrange actually wasn't Italian, despite of his French name. But it sounds French. It's enough. Fermat was left course Fermat. Was Weierstrass and Riemann, German. So again, you didn't see the Darboux theorem. So let's state it. Darboux, not only state, that's for the discussion. Darboux, may you rest in peace. I think that's how you write it. No, probably another A.
It's French. We can.
Yes.
Go.
Darboux theorem.
I know it's still second day, but yeah, whatever. It's French.
Yes. French is a waste of time. French states that.
You still say now.
What?
Parts. I thought you still say now. Everybody uses it.
I just want to hurt anyone's feelings. Anyone is French? Lev, are you French?
No, it's.
You like baguette, Lev? Theorem states that derivative of function, doesn't matter what a function is, can have only one kind, can be continuous. But Allah, that's how you write it, continuous. I don't know exactly. But you understand what I want to say. Can be continuous or have I call it main singularity. In other words, if a function is the derivative of another function, you cannot have a jump point where the limits from both sides are different and not a whole removable singularity. In other words, derivative can't have jump point or removable formal name, let's say whole point. Why exactly these theorems is true? It's something that I want to go in there, but trust me, it's true. Trust their book, even though it's French. So, yes.
What do you mean by major singularity?
A point where the function is not continuous.
There's a single code on the function.
We have three different types of singularities. The first one is whole. The function has something like that.
Right.
Both of the one-sided limits are the same and exist, just in the point itself. There's a problem. For example, minus 6 above x when it comes to 0. The limit is 1. We know that with the first clause was very fun. But in 0 itself, we put the button with 1 fine. And the second one is what I call jump, or first order singularity, when the limits do exist, but they are different. For example, 1 when x is negative, and -1 when x is positive, or something like that. And the third type of singularity, which is called lane, is actually formulates all the other words, that if a function has, let's say, a jump point, it is not a derivative of any function. When a function has a jump point, it doesn't have an antiderivative. With
Like for edit marks?
yeah, but not in a quotation way, but in a way of it's not exactly what I mean.
It's a kind of.
Kind of. Confusing myself. So let's finish my sentence. When a function has a jump point or a whole point, it does not have an antiderivative mathematically. Theorem, the French name states that.
Right. I mean, we're not going to go very deep into the theorem, probably. No. But can you, in few words, say what's the difference between a singularity and a whole, such that a singularity can have an integral or a derivative and a whole can?
As I said, that's very deep, but generally speaking, as you mentioned before, the definition of derivative comes with the limits. The limit of a fraction. Yes. And then the denominator tends to 0, and most of the time the numerator tends to 0 as well. So we have a question, what is the limit? Does limit exist? And most of the time when we come to this question of limits, okay, we can use L'Hopital or something like that. And the one option is there is a limit. The limit exists, the function is continuous. Good. The other option is that the denominator keeps to tend to 0, keeps on tending to 0, even though the numerator after one or two derivatives will use L'Hopital doesn't do it anymore. So when the denominator goes to 0, the numerator doesn't, the whole fraction goes to infinity or minus infinity or something like that. And these are the two cases possible when it comes to calculating the derivative or the definition of the limit. So this is something you can get when we derive a function. Well, of course, a continuous function like this very well when you derive it's the power of 3. You can get it, but the two other cases with a hole or with a jump, we can never get it when deriving a function. And yet again, we're not going very deep into this theorem, of course. So I just want to say write this sentence down. So a function with a hole or a jump point does not have an antiderivative. And just now I figured out that it's no fault. I started the list here, but just after one instant integral, I jumped to the second type of functions I mentioned in the start of this subject. So let's continue this list.
Why did you put the modular on the when you do that you pick up the value of that?
This function is defined for every x except 0.
Right.
And if I took the actual value away, this function is not defined, for example, in x minus 2. In x equals minus 2.
Okay.
But this function is. And I want to find a function where its derivative is this function for every x this function defined. So we put this actual value, and as I said, one can check for x negative, for x positive, that when you derive it, no matter what x, you get the happen thing. Another question? So let's continue this list very quick before we go to the third type of functions that we're going to talk about. So what else do we know? Let's say the integral of cosinus x. What function do we need to derive to get cosinus and sinus? And what function do we need to derive to get sinus? It's minus cosinus, cos. Faster. What else? What else? Let's say exponentials. Generally, when you have a in the power of x and you want to find the antiderivative, it's a to the power of x divided by ln a plus c, and specifically good old e integral of a to the power of x to the power of x plus this constant. I'll get used to it. We have two iffy and one linear algebra this semester. We'll get used to that left and right thing. What else? IV. It's common, it's important. The integral of one plus x squared, which are tangents. We can generalize this formula. Let's one above a squared plus x squared, and one can do it even more, but it's not important to me right now, so I'll just write in blue this case as well. And I count it as an instant integral. If you want to use it just like that in an exam or something, you can do it. And his friends, one above the square root of one equal one are singles. We can write some something the same with process. Yeah.
And just tangent,
What?
the antiderivative of a tangent that it exists. No.
It does exist, but it is not instant.
Okay.
Let's say that. Let's put it that way. And we're gonna get it very soon. I mean, let's say about this list of instant integral. I think it's enough. I already mentioned the functions that mathematically do not have a mathematical derivative. Now, third part of third type functions is functions that do have an antiderivative, but is not an elementary one. An elementary function is a function that is combination, sum or multiplication and stuff like that of all our nice functions from school, trigonometric and here exponentials and polynomials. And there are functions which are not elementary functions. The basic examples are, don't know how you actually say it in English, you only write it when you have 2 or 3 parts for the function. Here it's x, here it's minus x, functions like that. They are not elementary. We're going to see here in this course, let's say 3-4 weeks from now, another examples for functions that are not elementary. But right now, we are familiar with the elementary function, and when we ask, can we find an antiderivative, we had in mind an elementary antiderivative, like x to the power of 3 or x to the power of 2, etc., etc. So these functions, they're all functions that don't have an elementary antiderivative. For example, e to the power of x to the power of 2. It's a cute, sweet function. We know very easily how to find the derivative of this function, but I'll tell you, if you try very hard, but you will not find an elementary. Yet again, a combination of exponentials and trigonometric functions, etc., that when you derive it, you get e to the power of equal 1. Now it's a big question. When we look at a function, e to the power of equal 1, or mentioned earlier, tangent 6. Both are cute, not the simplest functions ever, but we know how to derive them very well. We're familiar. Probably solve the question or two about them in all of years of learning mathematics. What's the difference? Why does this function does not have a derivative, and this one does? So, as I said, it's a big question, and I don't think there is a full, complete answer to this question. But let me assure you that when we ask you to find the derivative of some function in the homework or in the final exam, the function you get is not going to be one of those functions that do not have an elementary antiderivative. If you do have an antiderivative, it's not elementary and not in the Futzeret way. As I mentioned, we're gonna lecture it by my plan. Lecture 7. Revolve, and we see what we get. So in conclusion, we're not going to face such functions, at least when we actually need to find the derivative, not because mathematically, somehow magically, we don't see them. Yet again, a simple, cute, sweet functions. When we want you to find the derivative, we'll give you a function that does have an antiderivative. And the core type of functions, it's what actually, where we actually put our interest, functions that one hand do not have an instant integral, not just x power 4. But on the other hand, with the field of effort, we can find the derivative of the function. I do a put my words. So we focus on functions that do have an elementary antiderivative. But are not instant. For example, Lani, so we'll see it today. Standard 6, we'll see next lecture or in the practice as I mentioned. And etc. And all the questions, all the exercise you're gonna solve, homework, practice. Here are a few examples that we managed to do, and of course, in the final exam, are going to be here. The part here in this type of function. Can't find the derivative, but let me put some work first. So what's our plan for the next 2-3 lectures? Cover as much as we can, but to cover different methods of calculating the derivative or finding the integral of function. And here, this lecture, I'm planning on showing one method. And next lecture, I'm going to see, as I mentioned, it's going to be Tuesday or probably next week with this but we're going to see another methods of finding the derivative. Two things before we actually show this method. One, any questions? Second, when it comes to derivatives, we had a lot of nice theorems, which we actually used when we proved our little proposition. We know how to derive some of the differentiable functions, how to derive the multiplication, the fraction of two functions, and composition, which is an important chain rule, important theorem from last course. We know how to do it. Do we have similar properties when it comes to integrals? For example, does the integral Oh, sum is the sum of integral. Well, you can, another word, you can say and derivative. Does the integral of multiplication is the multiplication of integral? It's not working that way when it comes to derivatives, but more generally, you can ask, do we have a formula to calculate the integral of multiplication of f and g from the integrals of f and g? And here comes the set part. The antiderivative is a linear operator, linear, I don't know what actually called when it comes to linear algebra. Operator is a nice word, but more than that, we have nothing. So when it comes to the properties of integral, think about it that way. But again, I want to correct me with just typos. We could do so. The integral of, let's say, f plus a and g, where f and g are functions and a is a constant, one can write it as the integral f plus a, the integral of g is linear. The linearity, oh, I don't know exactly how to say, and no more. We do not have any kind of formula to the integral of multiplication of functions, the integral of a composition, nothing. And that's one reason why finding the antiderivative that we only know that exists. The lecturer promised us we do have antiderivative in every question we need to answer, but he started to say it's much harder and difficult here than to find derivative. Even though conceptually they are the opposites, completing each other somewhere, really. Well, technically, it is. Hey, pizza. Here. Not that filter. No one see that filter. Okay, for this time, instead of the horror in his eyes. Huh? There was some little teenager holding a pizza. Yeah. So was afraid. Naked and afraid. Without a naked. I want to write it down on the board so we don't have any other property. Or it's something that is good enough to match board. Let's take notes. Going to have formula for integral של f כפול g, or integral של f הרכבת g, etc. You cannot just write it down. Which makes the task of finding a derivative difficult. Huh? Way sadder. Way sadder, but I always say that if we wanted to do an easier delay, VSC, we do. Why are we here? I don't know. Wrong reasons, right? But I want to go to the high-techs, right? Let the money flow. Let the cash flow. And it's totally fine. I'm always, it's not your first semester here, so we don't have this conversation. First lecture I have if you want to give it to students. I think it's Tuesday, the first lecture. I'm gonna be straightforward with that. You know, most of you, probably all of you, came here to, in Hebrew we say לסמנב, to put a V on these 3 years of courses and go find a job where you make, in Hebrew I call it orgazmin. Make a lot of money. And it's totally fine, totally fine. But feature, another feature of your journey is the difficult PSC. It's a difficult תואר ראשון. It was easy. The salary for the graduates, whatever how you say it, was of course smaller. So after I mentioned this and the properties, we can know that after we happen, only this for the thing of linear, we can start our first method and our only method for this lecture. I call it integration by parts. Integration by parts. And as I said, I don't want just to introduce you the method and example, but I also want to wear the practice hat for a little and try to explain to you why it does. Because I love to say it. Why, when we see a function, we think to ourselves, okay, we can use this method and not another method. We only think this one, so probably will be more interesting when we see other methods, but it's important nonetheless, even though we don't see them right now. So integration by parts. Integration by parts is based on the basic concept of derivative and multiplication functions. We know that. We know that. I use the letters F and G. Many other, for some reason, love the letters U and V for this test. Or if you read another text from the drive or Google, someone else, watch it a minute and do the YouTube and use U and V. So to define this letters. F times G plus FG F. And now we can say, hey, what happened when we put an integral on both, of course, both sides of this equation? So, if I here, and this time, this time, well, actually from left to right. Integral f g tag is integral of f of g plus the integral of f. Now, when it comes to this simple connection between the derivative and integral, it happens that they cancel each other. The opposite. So one can write that f and g without integral, is equal to the integral of f times g plus integral of g from f. And after you move, let's say, this integral to the other side of the equation, you get, this is where you put the rectangle, if one of the rectangle guys. The lecture you don't actually see this through the semester, but in the final exam, you see them. Rectangle guys. Yes, we put rectangle for every final line of the solution. Probably believe that somehow it's the point. So I call this line this formula integration by parts. When do we want to use this formula and how? Let's put it in my words. That's an example. And look at the clock. I'm gonna put two examples. Yeah.
Sorry, you put the derivative in G in both times. Does that make sense?
Oh no, it's probably just my it's not. So when we see the multiplications of two functions in our integral, By the way, the functions in the integral is called integrand. If you wanna, integrand. The A and G, A and D, sorry, in the end. If you wanna press the girl or something like that, you say, no, integrands. It's a I-class word. It's just the function inside the integral. So when the integrand is multiplications of two functions that, you look at the formula, one is need to be derived, and the second one needs to be integrated. Instead of f, we write f tag. Instead of g tag, we write g. When the integrand, the function inside, is written that way, we can think of the integration of parts as a good way to try to solve the exercise. I'm trying to be very cautious with my words. It's not magic. Yet again, it's not like derivative. When you have multiplications, you do A, B, C, and you get derivative. Integrals are much more complicated. The best we can do is try. But at least in the examples here in lecture, we'll probably not just try, but also succeed. Specifically, in another sense that you ask, specifically when you have multiplications of a polynomial and another function, polynomial with trigonometry, polynomial with exponential, etc., etc. Integration by parts is a good way to start, because when you derive polynomial, it becomes simpler. X to the power 2 becomes 2x, stuff like that. And on the other hand, the function that needed to be integrated is not g tab. We need to write g when it is an exponential or a trigonometric function. We easily know what the g itself should be. G tab is same of g. That's it. What do you want to ask?
Like I'm saying this, and I'm like, okay, we went from multiplication of functions to multiplication of functions. What you're doing here is like actually developing the multiplication, or
No, that's our final. That's the rectangle. Yes, that's our final line. But let's see. As I would say, a general description is beautiful. Take photos of your parents. It's all fun and games. But we must to see example, preferably examples, in order to start to understand. In Hebrew, I say that I thought like a lot of verbs. Fine, let's do an example. As integration by parts. Integration parts. We will do start. When we have multiplication. F O polynomial. Function. Example. Calculate and the derivative of x and simpsons multiply. Right. You have x. What functions can I derive again? It's not a simple question. So let's see how do we apply our method when it comes to this specific function. There is a question. Let's start. There are two functions. Which one we consider to be the G tag, which one is that? In other words, which function we're going to derive, which function is going to be integrated in our next step. Yes.
Or derive the f.
Yes. Why do we derive the x? What's the motive? Of course. Actually, great answer. When we derive the x, it goes to 1 and becomes simpler. That's our main interest. It's maybe we should emphasize it. When we use this integration by parts, after this equation, we do not finish the exercise. We switch our current integral with another integral, which we hope is going to be simpler, going to be easier to solve. So here we formally have this consideration to do. Hey, when derive this and integrate this, or vice versa. Actually, of course, we're going to derive the x. Get a more simple integral when we move forward to the next step. So I write it that way. Now notation. One can say in Hebrew or in English, whatever we're doing here, integration by parts, this six. More compact way to denote it is right here. Who is going to be f and who's going to be g? Actually, g tag. Here, you can write who is f tag is 1. And if g tag is sinus 6, g itself is minus cosine 6. Here we don't need to use the plus c, because, and it's something that's true for every exercise by integral. You write the plus c in the end, in the bottom line, in the rectangle. If you are the one of the rectangle guys, you don't have to take it with you, carry it with you along all the solution.
Yeah. Sorry. So here fg is an x times x. It's the integration of it. So like so g tag is times 6 and f tag is 6.
Yes.
No, wait.
Corre. Bravo. Agora nem está em velocidade.
So f like f and g is x and sin 6 or the same thing?
No, it's f and g tag.
Mm.
We consider arithmetic multiplication as f and g tag. And the question is, who do we choose to be f and who do we choose to be g tag?
Okay.
The right answer is f is going to be x. It's going to be simple in our next round. So let's write it slowly but surely. This way, we consider x to be f and sinus g tag. And by our formula, we have to get into the multiple. Fg without the integral, then minus the integral of f at g. So Fg is x minus cosine 6. I'll put the minus on the left already. Minus the integral of f at g, which is 1, and minus cosine. That's there we go. Minus 6. Cosine 6 minus we can take out the integral because it's linear, and the 1 right, so it's plus the integral of cosine 6. As I mentioned, do not finish the question, finish the exercise, find the derivative just by using integration by parts. The integration by parts, well, this example and similar examples gives us a singular integral. Instead of x sinus 6, which is f g tag, we get cosinus 6, which is f of g. What is the interval of cosinus 6? We know it's an instant one. It's sinus. One answer is minus 6 cosinus 6 plus minus 6 And do not ever forget the last thing when you finish calculating the underneath.
So yeah, trick or trick. Like someone fun.
It's a trick.
I mean, it's like it's an algebraic trick to like transform uh, what we know, which is the derivation of a composition,
Multiplication.
multiplication,
Yeah.
sorry, into something we know how to solve.
Yeah. You can use the word trick as the word method.
Yeah, I know.
Simple.
What I'm saying is that it's it's not something inherent to an integration. It's just like
Yes.
from derivative to make.
Yes. There are differences, but I like to compare it to the convergence tests of series from Infi1. I mean, you have the comparison test and Cauchy roots test and the Lambert מבחן המנה, etc., etc. And when you come to final exam, you get us at series in the question. And even not just part, but most of the solution is to understand which conversion test I'm going to use here, root or etc. etc. So it's the same. To put it that way, with integral. We're going to learn after. Another, just not one, other methods and the practice as well. And when it comes to the final exam, you get an integral. I want you to find a derivative. And you have to ask yourself, and it's actually big, not most of the solution, which method should I use? And this is just one. And I said, why do I use it here? Not just, we put a headline in individual parts. We're probably going to use individual parts. But because we see a multiplication of functions, and one of them is a polynomial. When you see a multiplication of functions, one is a polynomial, using integration by parts is the best shot we have. And again, it's not solving 100% of the time. And I want to show you in a little time that we're left another kind of function that individual parts does help us to find their derivative. But put it in that way in your head. When we see a multiplication of functions, especially one is a polynomial, I'm starting the solution with using integration by parts. What I want to say after this specific example, you can try. Probably it's going to be in homework or a different way. Let's try, first of all, x ln x. Fine, see if we can do it. Another similar example, but with a twist, is let's say x bar to the power of 2 sinus x. When you try to calculate the integral of x to the power of 2 sinus x with integration by parts, yes, you're going to have to do it one time. You choose as you choose wisely. Chose wisely. X bar what the function that we derive, which we denote by f in this lecture, and you'll get 2x. And then yet again, x with trigonometry needs integration of parts. So from now on, one can say, okay, we can have e to the power of n with sinus, tan, cosinus, whatever, and with enough integration by parts, we're gonna get it. Yes, but it's probably harder and okay, for l'hopital. But some, finding a recursion formula, probably a question like that will be normal. But so again, homework is near. He decides is a grown up, a big boy. I let him do it. We're really short of time. 1 minute. I want to show a different kind of example. A simple function, ln x. But by SQ, What is the antiderivative of ln x? In other words, which function you derive and get ln x? What do you answer? 3, 2, 1. It's not instant. What?
Like we said 1/x doesn't work. Like yeah.
Yeah. So the question is not if you know it, but if it's instant. It is not. It's gonna be x ln x minus 6 or something like that. I'm telling you, we're short of time, that I want to use integration by parts. And generally, you can say when I see an integral of, I call it a lone function. Integral of ln x, integral of arctangent 6, sinus 6, stuff like that, I use this method, integration by parts. But how? Where's the multiplication? Yeah? Multiply by 1. Of course. In Hebrew, I call it click shafel. How do we say it right in English? Shafel. Nefarious. I don't know exactly how to put it in a high level English. Um, it's not math. Come on. Every little child knows that when you multiply by 1, nothing happens. But you have to put it right where in the right place to use it correctly. So now when it's 1 in ln x, and we already finished, so let's do it quickly. You can choose the ln to be the function that you derive, and 1 to be the function that you integrate, and if the derivative is 1, the function itself is x. And now, with integration by parts, and I yet again help you with f and g from above, with a different from underneath, with a different color, effects. It is g tag in f. It becomes fg, which is x ln x, minus the integral of f tag g. This is fg. This is f tag g. X with x cancel each other, which is absolute gorgeous. We get x ln x minus the integral of 1. And the integral of 1, again, it's x. And then yet again, in the final answer, you write the plus c. Give you a complete, nice solution. So, 2 cases when we want to start and try. Try and be very humble. Solve integration by parts. First of all, when we see multiplication of a function, especially when one is a polynomial. Secondly, when we see a so-called lone function, integral of just ln x, just arctangents, and stuff like that. So we consider the multiplication with 1. And use the integration by parts that way. Any questions? What we did today? It was totally fun, but specific question? Elev, do you have any questions? Something you want to say? Everybody listens.
No, everything is good.
We love you, Lev. Lev to you. Yes, heart. Yalla, bye.